you. So unfortunately, I will not be presenting on the 135 years history of Gericke, but maybe tonight over a beer I can elaborate on that.
I have to go to bed.
Okay.
Well, that'd be very helpful, so Michael.
But,
Go ahead.
actually, I'm going to present about different PAT interfaces at the outlet of a continuous blender. A little disclaimer, I had nothing to do with this study. I didn't do any of the work. I didn't analyze any of the data, and I have no clue about PAT. Let's see if there's any questions. Please, Giovanna, help me out. Still, I'm going to start. So we have quite a long history at Gericke, more than 130 years, family-owned business, blah, blah, blah. 350 employees, and our focus has always been on powder handling and especially continuous feeding and continuous blending of powders. And we've been doing this for 70 plus years. However, we've always been doing that in the pharma industry more than 20 years now, and not very successful. Because we talked a little bit about change in pharma industry, and it just takes time for the industry to adopt. We have quite a lot of locations around the globe. I'm located in Switzerland, in Zurich. That's where our headquarters is located, and we have quite a lot of test centers around the globe. The closest one to Ireland is in Scotland. So if you want to do some trials with our equipment, please contact us, and we can run these trials. And just recently, we opened up a center also in Hyderabad. That's where we're not only doing trials, but we also do formulation development for our customers. And that's in partnership with a company called DFE Pharma, who are a lactose manufacturer.
Looks like there is a pin in my hand.
Yes, the blue pins are sales agents. He's useless. He will be visiting you guys on Thursday, so make up your mind yourself. Oh, he's a very nice guy.
He's still sober. No?
I know, probably not. He better be on Thursday because he's driving. So now let's go into continuous manufacturing of oral solid dosage forms, and I typically start this presentation with the batch process because that's what most companies and most people are familiar with. It somewhat starts with the dispensing of your APIs, your excipients. You start dosing them, or you weigh them out manually. You introduce them into a big blender, octagonal blender, bin blender. You blend them for a certain period of time, typically quite a long time, and then you bring it on to the next downstream process, which can be wet granulation, dry granulation, or direct compression. And in a very, very simplistic term, we are replacing these manual steps of batch manufacturing with what we call the Gericke formulation skid, or a so-called feeder blender unit. It's basically a skid-mounted system with so-called loss and weight feeders. These are screw feeders, and each of these screw feeders meters a constant stream of powders in the right ratio to each other. So you have one feeder for the API, you have one feeder for your filler, your binder, your lubricant, and they feed these in the right ratio to each other into a small continuous blender where we homogenize these powders, and then we can discharge them onto the next process step. And in between, we can have a little material diversion step. And that's also where we can integrate PAT tools. So oversimplifying, we basically replace the manual step of dispensing, feeding, blending, and some part of the quality assurance with one of these continuous manufacturing skids. And these skids are then integrated with various downstream processes. So in the most simple case, if you look at a direct compression process, we just put the skid on top of a tablet press, but we can use the same skid feeding into a roller compactor or into a continuous twin screw granulator for batch granulation. But this could also be capsule filling, sachet filling, hot melt extrusion, so virtually any continuous downstream process. And then typically we are not only kind of looking at a single unit operation like direct compression, but we also build so-called fully integrated end-to-end continuous manufacturing lines where you basically start here with the material dispensing. You have your first feeding and blending unit here for your intergranular phase. And we can go here in this case into a continuous twin screw granulator, continuous dryer. And then we have a second feeding and blending step where we can add the external phases, the lubricant, the super disintegrant. We go into a tablet compression machine and then eventually also a continuous or semi-continuous coating step. And that's how kind of the full process train of a truly continuous OSD manufacturing line would look like. As mentioned, we've been doing this for more than 20 years now in the pharmaceutical industry. So this actually extends another 10 years. The graph was still a flat curve. And then about 2017, that's when I started to take over at Gericke. You can clearly see the impact. No, it wasn't due to me. It was just, in general, it took quite a long time for the industry to adopt the new technology. And it's actually quite interesting because it was the FDA pushing companies to do continuous manufacturing. So discussed a bit of like people are worried to talk about change with the agencies, but now it was the agencies driving the change. So it's a bit contradicting. In the recent 10 years, we saw a wider adoption of continuous manufacturing. So we saw a number of more customers adopting it. And what was also quite interesting, it was some customers not only bought one line, but bought several lines and also bought lines for commercial manufacturing. So now it's slowly, the industry is like adopting continuous manufacturing, but still it's not happening on a wide scale. So most of the products out there are still manufactured in batch manufacturing. So let's go back into the continuous feeding and blending rate. So you have the feeders, the blenders, and then what I'm focusing on is the material diversion at the outlet of the continuous blender. Just to give you an idea how that looks like. So basically you have the continuous blender here discharging to a little thingy here, which we call the PAT stack. That's where we have the integration of the NIR sensor. And then right after that, we have a diversion mechanism. And this diversion mechanism kind of automatically switches based on the NIR signal, but it monitors some soft sensors like the loss and weight feeders, continuous blender, and the mean residence time of the system. And then basically, based on all of these factors, we can decide, are we producing good blend or are we producing wasted blend? Obviously, as you see, if you have the NIR here, it's critical on how that interface of the NIR to our continuous blender is. The one point is the software integration, which is key. And we have some experts on this here as well. You can just have your PAT instrument here as a standalone piece of equipment, but that's not something that you can actually use in a continuous line because you need to process that data from the spectrometer in real time to actually make a decision on the continuous blending. And then you can go for a little more what we call the basic integration, where the machine, so the PLC controller of the blender, talks directly to the spectrometer. Or you can have what I think, Brad, you're going to present tomorrow on is on a PAT management software, where you can actually collect a lot of more data, make a lot of more sense of the data of the individual spectra, etc. That's one side of the story. The other story is the mechanical integration of the NIR sensor. This is a little video we saw this morning by Giovanna. This is how we did it back in 2012. Funnily enough, someone 2024 did a scientific publication on it. Like, okay, a bit late, but already in 2012, we realized that just sticking the probe into a little chute without any mechanical wiping, without any sample presentation, leads to something like you see in the video. You see quite a lot of pulsation. You see the flickering light of the NIR sensor, and it's kind of obvious. I don't need to read a scientific publication that this is probably not the ideal integration of an NIR sensor. Another quite important topic I think Eric presented on as well is the sample size. And you can see if like you have pulsating powders moving past that sensor, it's very difficult to actually know how much sample you're measuring because you have no idea about the speed of the powder. You're not sure, are you measuring air, are you measuring powder? So it's also very important for the sample size calculation to have a good representative presentation of the powder in front of the NIR. And that's where we did the study together. And thank you for Joanna for doing all the work and also presenting all the data. We compared the Tasso with the U-Solis, and we challenged the system on, or at least we had a hypothesis that the U-Solis reduces the variability of the spectra, the signal to noise, and eventually also gives us more random or representative sampling in front of the NIR. How did we do that? So basically, we used the setup we just saw at the beginning with the NIR post to continuous blender. We ran 3 different blends with various concentrations of paracetamol or APAP, so ranging from 2.55 to 7.5%. And we had lactose and MCC as well as mexperiod in that blend. Of course, we used the Centronic center pad with 20 milliseconds at 150 positions, whatever that means. Again, I'm not a PAT expert, and the performance metric we looked at is signal quality, repeatability, and representability of the data collected. So we, as mentioned, we used the U-Solis. We had the chute, so the little box where we integrated the NIR at 30 degrees. That's kind of our standard setup. We did not vary that. We had the probe at the 1 o'clock position, and we ran at a relatively low speed of 10 RPM because we were running the blender also at a relatively low speed of 20 kilograms per hour. And then we compared this to the Tasso, where we had an acquisition time of 33 seconds. So it was 3 seconds on the NIR, 3 seconds off the NIR, and then switching back. And then spectrometer, which I mentioned to you. So these are some videos of the setup. On the left, you see the Tasso at the outlet of the blender. You saw the little spoon flicking, 3 seconds on, 3 seconds off. And then you can compare that to the U-Solis on the right, running at 10 RPM. So something you see in the lab, and we also see in various presentations. On the trial setup itself, we actually used pre-blended material. So we didn't want to see the variations of the loss and weight feeders or the continuous blenders. So we pre-blended the material. We charged it into a single loss and weight feeder, and that metered the material into the continuous blender and then discharge it on the NIR. So we could mimic kind of the discharge behavior of the continuous blender without worrying about any feeder variations or blender variations. Because I think someone had questioned this morning, this pulsation you saw on some of the videos that Novo presented, that's the discharge behavior of the continuous blender. And then also we waited about 2 minutes for the continuous blender to reach a steady state. So we didn't capture the kind of startup behavior of the continuous blender, and then measured for about 10 minutes. We did quite a long run compared to the studies where you manually poured the powders over the Tasso or the U-Solis. So first of all, Giovanna looked at the pure components, and this is actually a spectra from the blend. Oh, sorry, that shouldn't be doing that. And we could quite well distinguish between the lactose and the paracetamol. And also, which I unfortunately don't have on here, we also could see the wiper material. I think at 100, 1300 and 1700 nanometers. Then we also looked at all the raw spectra, and no idea what the spectra tells us, but you see a lot of variation here. You see a lot less variation here. And this was also after pre-processing, so we kind of removed everything where we didn't measure powder, but we measured air. And we also removed the interference of the wiper material, as well as excessive scattering or poor probe contract. But I think even me as a not PAT expert, you could see that you get a lot more consistent spectra with the U-Solis compared to the Tasso. So those baseline and signal to noise ratio was much better on the U-Solis. However, we also did a PLS model for the Tasso, and it was relatively okay, I would say. I mean, it's a linear curve, but we had an R square of 0.987, so it's not too bad. However, just to be aware that we actually had to exclude quite a lot of spectra from the Tasso because we had that inconsistent filling of the spoon. Then we also built a PLS model for the U-Solis, same lens, much nicer curve. But also the R square was 0.994, so a lot better than what we had on the Tasso. And if you compare the two PLS models within each other, so as mentioned, the R square is much better. The square arrow is also much lower and slope, still straight. But the intercept was also closer to zero, what you would expect. So overall, the PLS model on the U-Solis was much better than on the Tasso. Then we used that PLS model also to get some quantitative results on the three different API strengths. So it's 2.55, difficult to read, and 7.5. So you saw that spectra are, or the results are where you would expect. It's 2.5, 5, and 7.5, but you see quite a lot of variation in the results. And these are not kind of linked to any feeder variation or blender variation, because we're using pre-blended materials, and we knew that the blend we introduced to the machine was homogeneous. And we had an average error of, on average, 4.1% and a standard deviation of 5.6%. And then we did the same for the U-Solis, and you can see we get much nicer and flatter curves with the same materials, the same setup of the blender. So it's purely the kind of mechanical interface that has changed and has resulted in much nicer, flatter curves with an average error of 0.98% and a standard deviation of 1.25%. And if you kind of overlay the two graphs, like on average, we're there, but you see a lot of more variation with the Tasso compared to the U-Solis. So in quantified numbers, the average error was reduced by 76% and the standard deviation by 77%. So overall, our hypothesis that the U-Solis is a better tool to have at the outlet of a continuous blender was confirmed. And that's also kind of what we would recommend our customers to have instead of the Tasso. And one is that we have a more consistent powder bed in front of the probe. I think that's also something you saw in the videos quite well, where if you rotate at the right speed, you always get a good coverage of the probe. Whereas with the Tasso, you have to wait, then you flick, and then you have to wait again. And also, you are not measuring just a static bed when you're actually kind of holding the sample in front of, with the Tasso in front of the NIR, but you're actually moving powders in front of the NIR sensor. You get quite a lot more good spectra as well. As mentioned, the U-Solis would be the preferred solution as application at the outlet of a continuous blender. So thank you very much for this opportunity to present here, but my big thanks go out to Giovanna, who did the trials, to Uwe, and Sebastian maybe as well, and Fabian and Florian from my team, who did all the trial work that I present today.